Whiteboard Physics A-Level Lesson 64, Current and Charge. Yes, this is the first lesson of a new topic, electric current, and the first of the electricity topics. And we're going to start by talking about charge. Now, we have talked about charge as a quantity before. When we started the course, we introduced the idea of particles having charge. And remember, electrons were charged particles, and they had a charge of, let's put E equals negative 1.602 times 10 to the negative 19 coulombs. In fact, I'm not going to call it E, I'm going to call it Q instead, because we defined that as being minus E. And remember, protons, the charge of protons was equal to positive 1.60 times 10 to the negative 19 coulombs, or E. So, just out of interest, the reason why we use the letter Q is from the French quantité. It's quantité, electrical quantity. So that's the charge of these particles, and there are other particles as well, muons and kaons and so on and so on and so on. Now, when we talk about circuits and current flowing through circuits and things like that, which comes up a bit later on, we're not actually that interested in what particles are flowing. So we have a quantity called current, and we use the letter I for current, which is from the French intensité. So charge is quantité and current is intensité. Anyway, again, it's French. So we have current, which we can define as the amount of charge that flows past a point per second. And that's what we say. As long as the current is constant, then this equation works as our definition of current. Sometimes you'll see current written with delta Q, delta T. That's fine. Sometimes you'll see it written with D's instead, which allows for the possibility of a continuously changing current, a current that depends on time. But, let me change the color of that bit on my notes because we don't need to worry about that at this level. So let's just make that a lighter gray. And we've already sort of linked that to the idea that the integral of I as a function of t dt will be equal to Q. And that would be a delta Q, because it would be a Q plus some original amount when t was equal to 0. So there is that constant of integration, which I would have to add to this. But there we go. But that's beyond A level, so we'll leave that. So current, intensité, rate of flow of charge is how we could define it in words. Rate of flow of charge. And we need to learn that. But notice it's not rate of flow of electrons, or rate of flow of protons, or rate of flow of ions, or rate of flow of muons, or rate of flow of sigma particles, or whatever else. It's not that. It is just rate of flow of charge. So when we consider electricity, we're not usually that interested in what is actually flowing. Now, when current was originally discovered, and named intensité and all the rest of it, it was not understood at the time that current was this flow of charge. It wasn't understood. So current was originally defined, the intensity of electricity, if you like, but it was originally defined by the force that two wires will experience due to the magnetic field around those wires when current passes through them. And we will go into that as part of a later lesson. I don't need to do that now. But a little bit of history is going to help you understand why current is in the opposite direction to the direction that electrons flow in wires. We could take this a step further and talk about some real elementary stuff that you will have done in your GCSE. We could talk about if I take a rod of perspex and I take a rod of polycarbonate, so that's two different types of plastic, or we could take a rod of amber and a rod of glass. Doesn't really matter, glass or polycarbonate, and we could have amber or polythene, and of course there are other things as well, and we rub them with a cloth. Then what we find is that the two rods, which always have positive charges, as does the cloth, because they contain atoms which all have protons in them, there is a movement of negative charge. And in the case of amber, that negative charge flows from the cloth to the rod. So the rod will actually gain some negative charge. Whereas for the glass, the rod will lose some negative charge and the cloth gains negative charge. Draw a couple more minuses around the cloth. We can have an arrow here pointing in this direction to show that the electrons move in this direction and that the electrons move in this direction. Let's put E minus to make it clear that I'm talking about electrons. There we go. So glass and polycarbonate end up charging positively, and perspex, no, not perspex, that's polycarbonate, amber and polythene will end up charging negatively when you rub them with these cloths, and the cloths gain the opposite charge. So charge is conserved, it just gets transferred from one place to another. But this wasn't understood. So when early experiments into charge were happening, what happened was a man called Benjamin Franklin, famous for being one of the founding fathers of the United States of America, generally considered a polymath and a crazy guy when it comes to thunderstorms. One of the things he did is he experimented with charges, and he discovered that there isn't just one type of charge. It was understood that charge existed because the Greeks knew about this. Where you rub amber or you rub glass, small feathers or small leaves would be attracted to them. So the idea of some sort of electric influence was understood back in the time of the ancient Greeks, but it wasn't until Benjamin Franklin that it was figured out that there were in fact two different charges. It was identified that like charges repel and unlike charges attract. And we will go into much more detail about why that happens when we look at electric fields in year 13. But that was Benjamin Franklin's discovery. So he knew that different substances charge differently, and some charge positively and some charge negatively. Well, he chose to call them positive and negative because he was an accountant, an economist, and he saw things in terms of currency. And so he had this idea of this electrical currency flowing in this situation. And his idea was that when you rub amber with polythene, the electric currency leaves the amber, leaving it negative, and makes the cloth positive, and the electric currency flows in the other direction with glass. So he had the idea that when you rub glass, it gains electric currency and the cloth loses electric currency, and when you rub amber, the amber loses electric currency and the cloth gains electric currency. And what I'm calling electric currency came to be called charge. Why? Because what is a charge in finance is an amount of currency that gets moved from one place to another. That's where the word charge comes from, our English word charge. But it was only much later that it was discovered the particle that was transferring is actually the electron, and therefore the electron must be negatively charged in order for the amber that gains electrons to gain negative charge. It's the reason why we say electrons are negatively charged. It's because of Ben Franklin's allocation of amber as being negative. And of course, the Greek word for amber is electron, and that's where we get our name electron for the particle that the amber gains. So when we're talking about circuits, and this is absolutely crucial, current flows, I will say, and I'll waffle around that in a second because I'm not happy with that terminology. Current flows in opposite direction to electrons. And I actually, after this lesson, all the way through the rest of the electricity topic, I'm not going to bring that up again. That's just going to be understood that whenever I talk about current, I'm talking about something, electrical quantity, charge, Q, flowing in the opposite direction to the electrons flow. I'm talking about Ben Franklin's understanding of charge going this way and going this way. So maybe I should call that Q and Q. Maybe I need a different color. There is an effective flow of charge. One of the ways you can think about this is the idea of a financial transaction. I can give you money, which makes me poorer and you richer, or I could give you an invoice, a bill, although I have to be careful with the word bill because people in the United States of America call banknotes bills. A bill, an invoice. If I give you an invoice, what I've done is give you negative money. Your value has dropped because you have got this obligation to pay, and my value has increased. So I've effectively given you negative money. And it's that flow of invoices that we think of as being current. So in this notation here, we could say that, where am I going to write down? I'll write it up here, Q equal, no, I'll leave it. I was going to say Q equals effective charge flow, but I'll leave that. Right. So current is measured in amperes. That's no different to GCSE, so it's barely worth us writing that down. It's no new information there. And I have an issue with talking about the direction of current because current is a scalar. And you can tell current's a scalar by looking at this equation here. Just got the square thing still highlighted. By looking at this equation here, you can see that charge divided by time. Charge is a scalar and time is a scalar. Therefore, current has to be a scalar. So current's a scalar, not a vector. How can it have a direction? But we think about it as being sort of a pseudo-vector. It is vector-like in a sense, because there is something flowing and that has a direction. What's flowing? Well, charge. Yes, electrons are flowing one way, but it doesn't matter. We can visualize it as the effective flow of charge in the other direction. But it doesn't have to be electrons, of course. In an electric circuit, we could have a battery of cells, and there's some electrochemistry happening in those cells, which means there is a flow of ions, and that's a current. Or we could have a particle beam that's protons, that's a current. Or I could rub a balloon on my head and kick it across a room. That's a charge that's flowing. That's a current. So it doesn't have to be electrons flowing. In lightning, it's not electrons flowing, it's ions. That's ions flowing and colliding, causing that heating up of the gas that we see as the spark. So anyway, that's not the whole story of what the spark is. It's a lot more involved than that. So current then, current rate of flow of charge. We're now going to move on to how fast that charge moves in a circuit. Now this topic is often missing from textbooks, and it really shouldn't be, and this is the right place for it. Drift velocity. So I want you to imagine that we have a wire, and I will do my best to quickly sketch a wire. I'm becoming quite proficient in copying and pasting and quite rapidly trying to draw things now, especially now that I have fixed the built-in pen docker thing on my Chromebook that I'm writing this on. There we go. And I will erase part of this. Oops. There we are, that'll do. There's a wire. And the wire has certain dimensions, and I'm going to use, let's use green for those dimensions. We've got a length of the wire, which we can call L. Let's just do this. L. The area, there has a cross-sectional area A. Let's imagine that it is cylindrical, so we could work out, we could use a diameter, but I'm just going to use cross-sectional area. That's the cross-sectional area of sort of this face here. So maybe I should move that label cross-sectional area to the other side then. And that wire contains charges, lots of them. And these charges are going to flow. Now, we can talk about electrons, of course, we can talk about electrons, and those electrons, let's imagine that those electrons are all going to be flowing in one particular direction. I'm going to use a different color for electrons now. I'm going to use blue for electrons, because I use blue for electrons just above. So we've got loads of electrons in this wire, and they are going to be flowing, and they are all going to be flowing in one direction. Let's say they're all flowing to the right. So what that means is that if I sit here and I watch here, then I'll be able to count how many electrons go past me per second. Or it should be the same number as if I sit here and watch electrons go past, because electrons don't disappear, they don't cease to exist. Every electron that passes the left-hand side of this wire should also pass the right-hand side of this wire if we leave it long enough while we're watching. So let's have that I'm watching it where the eye is, and I'm counting how many electrons go past. Well, each electron carries a certain amount of charge, negative 1.602 times 10 to the negative 19 coulombs. And that's effectively the same as that same amount of charge flowing in this direction. And we usually think of that as being a current to the left. But we could actually calculate what the drift velocity of that charge is. In other words, I could work out the drift velocity of these electrons. How fast, on average, are they drifting, and that's a clue to how big it is, are they drifting through this metal? So we need to have some information. We haven't got enough information here. We need to know how many electrons there are per cubic meter of metal. And we can call this the charge density. And there are different symbols we could use for charge density. What symbol should I use? I might use rho for charge density. You might use an eta instead. I'm going to use a rho because it's the symbol I use for density anyway. So if you use a different symbol, that's fine. I'm going to use that for charge density today. Density, or we could use a mu, I suppose. Anyway, let's say that this is some sort of copper wire, and the charge density in this is in the order of, or the electron density, I should say. The electron density is in the order of 10 to the 29 electrons per cubic meter. So let's not call it charge density, let's call it electron density. Rub that one out. And let's say that is electron density. And actually, in terms of symbols, I could just call that number of electrons divided by volume. I could just call it that, couldn't I? Number of electrons divided by volume is the electron density. And I know what the electron density is. In fact, I think I'll use a lowercase n for electron density, like that. So I'm going to say lowercase n is electron density, I think that might be consistent with what we use in Isaac physics. I'm going to say n is number of electrons, and V is going to be equal to AL, which is the volume of this particular column of wire. And what we're going to calculate is how fast the electrons drift through this wire. Now, the electrons actually are going to be moving very fast, very, very fast, and they're going to be bouncing around all over the place, a bit like the way molecules in the air are traveling between 400, 450 meters per second. They're very fast indeed. You don't really feel that. I mean, you do in a sense because of air pressure, but you don't feel that. When there's wind, there's an average velocity for those molecules of air. When there's no wind, the average velocity is 0. But the velocity, the speed, the average speed, and there's a type of average called root mean squared we'll get into the future, but not right now, is around about 450 meters per second. So it's the same with this. The electrons are moving actually very fast, but they're drifting very slowly from left to right. And we're going to see how quickly they drift. And so we know that current, I, is equal to the current, like that. Now, the total amount of charge that is flowing per second is the current. So that is Q divided by T. The total amount of charge that crosses that point. And the total amount of charge is the number of electrons multiplied by the charge of each electron. But actually that number of electrons times the charge of the electron, I could do a minus there because E would be the elementary charge, which is positive, so I should put a minus in there. But it doesn't matter. It doesn't matter at all because we're looking at flow of electrons rather than flow of charge. So rather than flow of charge that consists of a current. So I'm not bothered about the negative signs. For this, I'm just trying to derive an equation. And how many electrons have I got? Well, the number of electrons I've got is the volume, the electron density multiplied by the volume. Okay, so n, little n, is how many electrons per cubic meter, and V is how many cubic meters. And I end up with something like this. And what is the volume? Well, the volume is going to be A multiplied by L. And here's the exciting bit. L over T. Let's just move this down a bit so I don't get in a muddle. There we go. L over T. Well, L is the total length of this wire. And T is the time it would take for that amount of charge to pass where I've drawn the I. So in other words, L over T is the average velocity of the electrons. There we go, and there it is. There's my equation. If I know the electron density, I know the cross-sectional area of the wire, and I know the charge of each electron, which I do. I know the current, I can calculate V. V is the drift velocity. So drift velocity V is equal to I divided by NAE. Put them in any order you like. And of course, if this is a cylindrical wire, that could be equal to quarter pi d squared, where d is the diameter of the wire. So all we're doing there is saying A is equal to a quarter pi d squared for a cylinder. But it might not be a cylindrical wire. But if it is, then that's what we can say. So let me just change the color of this, but just in case we're not dealing with cylindrical wires, let's use blue. And that's our calculation of drift velocity. We could plug some numbers in. So for a typical circuit, we might have a current in the order of less than an amp. Let's be generous and say 0.5 amperes. We might be using a copper wire, so N is around about 10 to the 29 electrons per cubic meter. What would the diameter of a wire be? Maybe a millimeter, something like that. And the charge of the electron, we already know, is 1.602 times 10 to the negative 19. Don't worry about the sign on that. So we can take those data and plug it into our equation. So V would equal 4 times 0.50 divided by pi, also divided by 10 to the 29, also divided by, why have I written that in millimeters? That's about a millimeter. So let's just write that as, that was clumsy, wasn't it? 1.00. Let's just do one significant figure, two significant figures, millimeters. So that's that times 10 to the negative 3. That's what the milli is, 10 to the negative 3, and then it's squared. And then times by 1.60 times 10 to the negative 19. There we go. So if I take my calculator and I chuck all that in, how fast are these electrons going to be moving through this wire in this pretty common circuit? So if you'll indulge me for a second whilst I type a bunch of numbers into a calculator, which you can't even see what I'm doing, so it's not the most exciting thing to listen to me doing, but I'm doing it anyway. Squared, divide, and I'm using reverse Polish notation, so it's a little bit quicker for me to do. I get around about 3.98, so we'll round it to 4.0 times 10 to the negative 5 meters per second. So that's not very much at all. In terms of millimeters per second, that's going to be about 4 times 10 to the negative 2 millimeters per second. And then, of course, in terms of microns per second, that's about 4, well, we could just write that as 40 micrometers per second. So that's really tiny as a distance per second, the average drift velocity of these electrons. So clearly any model of circuits that we have where the electrons trundle around the battery, pick up energy, then trundle all the way around to a light bulb and drop off that energy are nonsense, because it's going to take way too long for those electrons to get from one side of the circuit to the other. They're barely moving at all, or barely drifting at all. And I think that's all I need to talk about for this. I mean, we could talk now about conductors and insulators, I suppose, but then that ties nicely into resistance. But let's just put it in here for completeness. So conductors are ones where charge can flow. Charge can easily flow through them. Insulators, charge cannot easily flow through them. There is also something called a semiconductor, and these are interesting. It doesn't just mean they're not very good conductors. These are much more interested than that. So in a semiconductor, we can get more charge to flow per second, so more current under certain circumstances. And I'll leave it there for now in the notes. What happens with semiconductors is the number of free charges per unit volume, the charge density, the electron density, depends on things like temperature. It can depend on light intensity level. It can depend on pressure, I guess. It can even depend on current. So more current can actually change the number of charge carriers there are per cubic meter. So they're interesting. Semiconductors are very interesting materials indeed. But we'll leave that there, and we'll talk about potential difference and power in the next lesson. Hope you found that helpful.